Hi guys, good day. We're back again for another video, and this time we're gonna talk about angular modulation. So before we get started, first, what is angular modulation? Angular modulation or angle modulation is the process in which the frequency or phase of the carrier varies according to the message signal or modulating signal. There are two types of angular modulation. First one is called the frequency modulation, which is defined to be the encoding of information in a carrier wave by varying the instantaneous frequency of the wave. The second type is called the phase modulation. Phase modulation, or PM, is a modulation pattern for conditioning communication signals for transmission. It encodes a message signal as variations in the instantaneous phase of a carrier wave. So before we go through the concepts of the two principles of angular modulation, we first compare the frequency modulation and phase modulation to amplitude modulation. So to start, in terms of definition, amplitude modulation is defined that in a way that the amplitude of the carrier varies in accordance with the amplitude of the modulating signal, keeping frequency and phase constant. In a frequency modulation, frequency of the carrier varies in accordance with the amplitude of the modulating signal, keeping the amplitude and phase constant. And for phase modulation, phase of the carrier wave varies in accordance with the amplitude of the modulating signal, keeping amplitude and frequency constant. Our next parameter is noise. For noise in AM receivers are very susceptible to noise, while for FM, noise immunity of FM is superior in comparison with those of AM and PM. While in phase modulation, noise immunity is better than AM but not FM. So for the functionality, in AM, the amplitude of the carrier wave in AM diverges as per amplitude or voltage of modulating signal input. In FM, the frequency of the carrier wave deviates as per the voltage of the modulating signal input, while for phase modulation, a phase of the carrier wave varies as per the voltage of modulating signal input. So in terms of constant parameter, in AM, the frequency of the carrier wave is kept invariable. In FM, the amplitude of the carrier wave is kept changeless, while in PM, the amplitude of the carrier wave is kept changeless also. So to visualize what is their difference, for FM, we can see in this graphic photo that for the signal in AM, the amplitude varies, while in FM, we can see that the frequency varies. Then for phase modulation, this is how it works. So to have an in-depth discussion of frequency modulation, we have here its mathematical expression. It is expressed as y of t is equal to a sub c cosine of 2 pi times the integral of f of tau times its derivative from t to 0. It can be expressed also as a sub c cosine of 2 pi integral from 0 to t of f of c plus f delta x sub m of tau. Then it can also be expressed as a sub c cosine of 2 phi f ct plus 2 phi f delta times the integral of xm tau from 0 to t, wherein AC is the amplitude of the carrier signal, f sub delta is known as the frequency deviation. It can be expressed by k sub f times a sub m, wherein k sub f is the sensitivity of the frequency modulator and a sub m being the amplitude of the modulating signal. So f of tau is known as the instantaneous frequency of the oscillator. X sub m of t is the baseband signal or the carrier signal, and f sub c is the carrier frequency. The next one is the expression of the baseband signal x sub m of t. It is mathematically expressed as the integral of x sub m of tau to its derivative from 0 to t is also equivalent to sine of 2 pi f sub m of t all over 2 pi f sub m, which simplifies the fm equation into y sub t equals a sub c cosine of 2 pi f c t plus the ratio between f sub delta and f sub m times sine of 2 pi f sub mt. In this simplified equation, the amplitude of the modulating signal a sub m is represented in the frequency deviation. For the modulation index of frequency modulation, as in other modulation systems, the modulation index indicates by how much the modulated variable varies around its unmodulated level. It relates to variations in the carrier frequency. It can be expressed as m equals frequency deviation over modulation frequency. In mathematical terms, it is the delta of f over f sub m. When m is greater than 0.5, frequency modulation is classified as wideband FM. While when it's less than 0.5, frequency modulation is classified as narrowband FM. For the percent modulation of frequency modulation is equal to the actual frequency deviation over the maximum allowable frequency deviation. Next part is the FM deviation ratio. We can express this as capital M, wherein it is equal to the max frequency deviation divided by the max modulation frequency. For FM equations as Bessel function, FM equation is given by B sub Fm of t equals Vc cosine of omega ct plus m sine of omega mt. Using trigonometric identities of cosine a plus b, it will be equal to cosine of a times cosine of b minus sine of a times sine of b. The equation then becomes b sub fm of t equals to Vc cosine of omega ct times cosine of m sine of omega mt minus Vc sine of omega ct times sine of m sine of omega mt, where cosine of m sum of m times sine of omega m sub t and sine of m times sine of omega sub m of t is a trigonometric series called as Bessel function. So this material here is made by N. Hassan, entitled Principles of Communication System. So to go over with the Bessel function, equation 1 is then expanded using Fourier series. Thus it becomes the equation here on the first equation is when n is equal to an even number, and the second equation is when n is equal to an odd number. So further simplifications of the Bessel function. then it becomes B sub Fm of t is equal to E sub c times the summation from negative infinity to infinity of j sub n times m times cosine of omega c plus n times omega m times t. So expanding the equation yields this equation, wherein the first term is the carrier band, then the next to it is the sideband 1, then sideband 2, and up to sideband n. So that is the FM equation in Bessel function. In that equation, m is equal to the modulation index, Vc is equal to peak amplitude of the unmodulated carrier, J sub 0 of m is the carrier component, J sub 1 of m is the first set of side frequencies displaced from the carrier by omega m, J2 of m is the second set, and J sub n of m is the nth set of side frequencies displaced from the carrier by n times omega sub m. So here is the representation of a Bessel table with the column representing the modulation index, while on the upper part is the sideband pairs. FM bandwidth can be calculated, or let's say approximated. First case is the narrowband FM. It is defined as the condition where beta is small enough to make all terms after the first two in the series expansion of the FM equation negligible. So bandwidth is approximately 2 times omega sub m. For a wideband FM, it is defined as when a significant number of sidebands have significant amplitude. So bandwidth this time is approximately 2 times delta of omega. Also, FM bandwidth calculation methods can be done by the Carson's rule, wherein bandwidth is equal to 2 times delta f plus f sub m. Then finding the actual bandwidth using the Bessel table, bandwidth is equal to 2 times n times f sub m. So power calculations in FM signal. Unlike AM, the carrier power of FM is redistributed among the carrier and sidebands. Thus, the total power is P sub T of FM is equal to P sub C, wherein P sub T is equal to the summation of the power at sub 0 up to sub n, wherein P sub 0 is the modulated carrier power, P sub 1 is the power in the first set of sidebands, P sub 2 is the power in the second set, while P sub n is the power in the nth set of sidebands. We must take note that Pc is equal to Vc squared over 2R, and P sub c is not equal to P sub 0. P sub c is unmodulated carrier power, P sub 0 is unmodulated carrier power, and R is the load resistance. So to simplify that, power in FM signal, total power in FM wave is the summation. Thus we can write it also as P sub t is equal to B sub 0 squared over 2R, so on and so forth until we reach the nth term. In this case, V sub 0, B sub 1, and B sub n are FM modulated carrier amplitudes and sidebands amplitudes respectively. Then R is the load resistance. Thus, we can use Bessel table and further improve the equation to this one. And then, using this, we can calculate the total power in an FM signal. The frequency modulation in time domain looks like this. So, here is a graphical representation of having the same inputs of signals for an index of 1. So we can see we cannot see how the frequency modulated wave changes. So by increasing it, we can see that in here the frequency becomes more compact at certain sections, so we can visualize clearly the frequency modulation. So in the frequency domain of a frequency modulated signal, this is how it looks. For modulation index of 1, and then for a modulation index of 4, the number of significant sidebands increase. So the FM sidebands can also be interpreted like this one in frequency domain, wherein the middle part signifies the carrier frequency. Then from the leftmost part, it is equal to f sub c minus 3 of fm, and then f of c minus 2 of f sub m, then f sub c minus fm, and then on the right side, it's just the addition. It's the counterpart of those in the left side. In this case, bandwidth is 6 times fm. Next principle is the phase modulation. Phase modulation changes the phase angle of the complex envelope in direct proportion to the message signal. So if m of t is the message signal to be transmitted, and the carrier onto which the signal is modulated is c of t equals to a sub c sine of omega ct plus phi sub c. Then the modulated signal is y of t is equal to a sub c sine of omega c times t plus plus m of t, and then plus phi of c. This shows how m of t modulates the phase. The greater m of t is at a point in time, the greater the phase shape of the modulated signal at that point. It can also be viewed as a change of the frequency of the carrier signal, and phase modulation can thus be considered a special case of frequency modulation in which the carrier frequency modulation is given by the time derivative of the phase modulation. So PM changes the phase angle of the complex envelope. So m of t is equal to cosine omega ct plus h times omega m times t. So the mathematics of the spectral behavior reveals that there are two regions of particular interest. For small amplitude signals, PM is similar to amplitude modulation, and it exhibits its unfortunate doubling of baseband bandwidth and poor efficiency. For a single large sinusoidal signal, PM is similar to FM, and its bandwidth is approximately 2 times h plus 1 times f sub m, wherein f sub m is equal to omega m over 2 pi, and h is the modulation index defined in the following section. So for the modulation index of phase modulation, as with other modulation indices, this quantity indicates by how much the modulated variable varies around its unmodulated level. It relates to the variations in the phase of the carrier signal. It is expressed mathematically as h is equal to delta of pi, wherein delta of pi, or should I say delta of theta, is the peak phase deviation. Percent h, or percent modulation, can be calculated by getting the ratio of the actual phase deviation over the maximum allowable phase deviation and then multiply it to 100. Phase deviation is can also be expressed as delta of omega sub pm is equal to k sub p times E sub m times omega of m, wherein k sub p is the proportionality constant, E sub m is the modulating signal amplitude, and omega sub m is the modulating signal frequency. Phase modulation in time domain can be visualized as follows. While in its frequency domain, for a 1 kHz sinusoidal baseband signal in a 10 kHz carrier, its phase modulation is visualized in this graph. So that's it for our video, and thanks for watching.